Hello, everyone. I am Josh Fitzgerald. I'm from Heliax. I'm going to present to you VampIR, our programming language for arithmetic circuits that is universal and is not tied to any specific backend or proof system implementation. So yeah, we're calling it like LLVM for polynomial circuits, meaning that we have one representation for arithmetic circuits, which can serve as a target for front-end languages, and also can be used in any proof system backend as well. So if you can compile into VampIR, you can take advantage of any proof system backend that you would like, and you can also choose from a whole slew of front-end languages as long as there's a compiler to VampIR. So this is a workshop. I'm hoping to make this very interactive, and I'll be live coding up here. If you want to live code yourself, if you brought a device, you can join the workshop code space. So there is a QR code here that should take you there. If you can't get that on your device, you can go to Anoma's GitHub, find the VampIR repo. There's a branch called EthCC6. Click on the code button, and it should show you a code space called symmetrical xylophone, which you can use to code along. You'll have the same version of VampIR that I have, and it even has some syntax highlighting as well. Okay? So I'm going to leave this up a little bit while I give kind of an introduction to VampIR, just to give people a chance to use it if you want to. At Heliax, we want to use zero-knowledge proofs in our stack. And our main goal with our stack is we want things to be not monolithic. We want to be able to let people spin up all sorts of different blockchains with different security concerns and different properties, including privacy. If you want privacy, then you can use zero-knowledge proofs, snarks, starks, etc. But there are all these different proof systems to choose from, each with their own properties, and different implementations of those proof systems which also differ. And that presents a problem for us at Heliax in building a NOMA, because we want our stack to be as open as possible, meaning you're not forced to choose a particular proof system. If you want to use a proof system that has different characteristics that fit your use case better, you should be able to. That's how we think of it. So that means we need a way of expressing our validity predicates, which is what we call them on a NOMA, in a way that is universal for all proof systems. Okay. So I'll give just a little bit more intro. Then we're going to be doing some live coding. We may or may not finish the live coding portion. We're going to be looking at the Blake2S hash and coding up a circuit in VampIR for Blake2S. We'll be compiling it. We'll be creating proofs and verifying our circuits as we go. If there's time left, I'll give you a little progress report about where VampIR stands now and where to go if you want to get involved. Okay, so I've covered this a little bit already, so I'll try and go fast. We have this project called the MASP. It's the multi-asset shielded pool. It is a component of our Namada chain, which is in development right now. The MASP was written a few years ago in Bellman, and it uses the Groth16 proving system. We were interested in taking our MASP and adding something like recursion to it. So we were interested in looking at Halo 2. Can we use the MASP in Halo 2? We were also thinking about using Plonk without recursion, maybe to get some better efficiency. So we were wondering, can we write the MASP in Plonk or PlonkUp or UltraPlonk, which has lookups? So I tried rewriting the MASP in these other proof systems, and it turns out to be quite difficult to do by hand. There's also lots of problems because something that's nicely audited, like the MASP, in a certain circuit format, when you apply transformations by hand to rewrite it in another format, you could introduce new bugs that you don't see. And it's actually quite tricky to do well, and it's also tricky to do efficiently. So what we wanted is to be able to write a circuit like our MASP in a universal format like VampIR, and then we can have that circuit be audited and tested very well, and then we can take that and port it into any backend that we choose. That also lets us compare different backends for speed and efficiency and so on. And something else we would like to do is have a nice target for front-end languages as well. We have a language called Juvix, which is a dependently typed functional language similar to Haskell. And we can compile from Juvix into VampIR and then prove circuits with a couple of different backends right now. Theoretically, we can compile to and from other circuit IRs like ASIR. ASIR is the intermediate representation for circuits in Noir used by the Aztec team. So, and we also have AirScript as another possible target for compilation to and from VampIR. And with ASIR and AirScript, for instance, we could write a circuit in Juvix and compile it in Beretenberg or Bellman, PlonkUp, Halo 2, or Winterfell, or any other thing that we write a compiler for. We could also, or someone could write a compiler from, say, Socrates into VampIR, and now circuits written in Socrates have access to all of these different backends. Okay. Arithmetic circuits. These are the objects that VampIR describes. An arithmetic circuit is a representation of the computation of a polynomial. So I have two arithmetic circuits here. Both have 5 variables. And if you look at the equations down here at the bottom, you should see that they're actually the same polynomial, but they're computed differently. This one on the left is more simple because it's been factored out, right? But they're actually the same. So these are two different arithmetic circuits, but they represent the same polynomial. So yeah, arithmetic circuits represent a computation of a polynomial, not a polynomial itself. You should also see how these circuits, they're not like functions. They don't have inputs and outputs. They just kind of have inputs, and they either satisfy the circuit or don't. Okay. So that makes it a little weird. We're very used to using functions in programming. But with arithmetic circuits, you kind of have to simulate functions because they don't naturally have them. Okay, arithmetic circuits can be joined by wiring them together. And it's like literally what you would expect if you had an electronic circuit and you wired two contacts together. Those contacts will have to have the same voltage or whatever, right? So here's two circuits. One does div mod, and the other does range 4. That's so it's checking to see if something is 4 bits. And if you take the remainder of div mod and connect it to Z over here in the range circuit, you're showing that the remainder from div mod is 4 bits, because R and Z have to have the same value. Okay. Arithmetic circuits can also be thought of as a system of polynomial equations, or a way of computing a system of polynomial equations. So all of these circuits can be represented with polynomials like here on the right. And this is the format that we choose to represent them with in VampIR. Okay, so that's the end of the intro. We're going to proceed with live coding demonstration. We're going to be looking at the Blake2s hash function. You can find the spec to Blake2s online. I've got the URL right here. I've got the most important parts for us today up on the screen. We're going to be writing a circuit that checks correct computation of function g. If you look at function g, what it does is it takes a vector of 16 words. A, B, C, and D are actually just indices of the 4 words that we are working with in this round of the function. Each round you do a different operation on a different set of the 16 words. And X and Y are pieces of the state that is getting folded into all of this. Okay, so you can see what we do. We're taking the 4 words, which are V of A, V of B, V of C, and V of D, and we're doing a couple of simple operations, adding them, mod 2 to the 32, W is 32, as you can see over here, doing a rotation, and XOR. So we need to write circuits that do addition, mod 2 to the 32, rotations of different amounts, and XOR. Okay. If we can get all of those, then we have our function g. If you look at the Blake2s spec, function g is like the core of everything. It's done many times, but there's not much else to the hash function beyond function g. It's like the most significant part of the hash function. We probably won't get through the entire function g, but we're going to try. Okay. This is a simple definition in VampIR. We call them aliases mainly because it let me get a letter A in a convenient spot in an acronym for VampIR. But the definition is a name followed by the inputs, equal sign, you have curly brackets. In the body of the alias, you have expressions that end with semicolons, and at the end, you have a return value, that's the out, with no semicolon. And finally, after the curly braces, the closing curly brace, you have another semicolon. So we do a lot of what we're going to do today is defining these aliases. Okay. Here's an example. This is the function that constrains an input to be Boolean. So we have def bool x. Then there should be an equal sign in there. Then we have x squared equals x. That's an expression that constrains x to be equal to its square. The only 2 solutions to that are 0 and 1. And then this also returns x. That's mainly for convenience, because you may want to combine some lines, do a little inlining there. You wouldn't have to return x to constrain x. Okay? But this one returns x, which is nice. Then below that, you see bool a. This is a constraint expression that's using this definition. So what that will do is allocate a new variable a and add a squared equals a into the constraint system. Yes?
Does there exist some similar things to work on extension fields, or are we only working over GF2?
VampIR uses big integers, which can then be reduced into field expressions later. VampIR itself is not aware of fields. It's basically integers only. It works in integers. VampIR itself does not have any awareness of finite fields.
Okay, so you have to re-implement it starting from here? If you want to build a...
So like later in the compiler stack, the integer representations are converted into like finite fields. But each proof system uses different elliptic curves. They have different like base fields and scalar fields. So VampIR itself, trying to be agnostic to that stuff, it doesn't use finite fields in the language itself. If you wanted to simulate finite field arithmetic in VampIR, you can do that using modulo and that kind of thing. Is that
Mojo?
Modulo, like just modular arithmetic. You can use that to simulate finite fields, although it's a bit expensive in VampIR.
Okay.
Usually you want to avoid doing that if you can.
Okay.
Okay, just one more concept I want to make sure that we look at is this keyword called fresh. An arithmetic circuit is not, it's not really a program. It does not know what values are inside these variables. And so it can't like compute values that need to go into these variables. In a zero-knowledge proof system, the prover needs to compute all the values of all the variables that they are submitting as part of their proof. So the prover needs to know how to compute these. VampIR, if it were only polynomials, only these constraints, wouldn't know how to do this. So we have fresh. There's a similar concept in CIRCOM, I believe. They've got a symbol for this. But what fresh does is it allocates a brand new variable, fresh variable, and the expression inside the parentheses tells the prover later on how to compute that variable. Fresh does not create any constraints. So you have to be careful with using fresh. Just because we have fresh x mod 2 does not mean that x will actually be, or that b0, I guess, will actually be x mod 2. It's not constrained. If you just use fresh, you're just creating a new variable. The bool that I've put in front of fresh actually applies the constraints. Does that make sense? Fresh does not create constraints. You have to apply the constraints separately. Okay? All right, there's more in this presentation. Oh yeah, we can do some cool stuff like currying, and we have tuples. I'm going to kind of fast forward through this. We have lists. We can find heads and tails of lists. We can even iterate over lists. We may not be using some of those features in our live coding, but we do have them. Pretty cool. Okay, so I'm going to switch to the live coding portion now. Okay. Oh, good. Okay. So I'm just going to create a file for us to work in. Let's see if I can find it over here. All right. How does this look to you? Can we read that? Even up there? Okay. Good. All right, so let's start with our first definition. I will be switching back and forth with the Blake 2S spec that I had up here earlier. Let me get that prepared. Okay, so there's that. We need to do addition mod 2 to the 32. So we're going to start by working on that. When you do mod 2 to the 32, well, when you do mod at all, the result of modular division needs to be within a certain range, right? It's not correct if it's larger than the divisor, right? So we need range proofs in order to do modular division. So we're going to start with some range proofs. The simplest range proof is something we've already seen, which is constraining x to be 0 or 1. That shows x is 1 bit. Right? It's a range proof. So I'll quickly just get this going. Should be the exact same as what we saw before. So def bool x equals, in curly braces, x squared equals x, and then we're going to return x as well. That lets us use x in, we can compose this with other stuff and use x. Don't forget semicolon at the end. And now that we have a definition, we can apply this constraint to variables if we want. So to do that, I'm just going to write bool y with semicolon. Bool y with a semicolon, this is an expression. It is a constraint. It will apply this bool definition to y, meaning that y must be a Boolean. So we have a circuit here. It has one variable, y. And what this circuit does is check that y is either 0 or 1. Okay? So we're going to go ahead and compile this and create a proof and then verify the proof. And then we'll come back and put some weird value in for y and show that the verification fails. Okay? So let's see. Does this have my history in it? Oh, no. Okay. So the command we're going to use, if you're in the code space, you can use VAMP-IR for VampIR. I'll just show you we have a helpful CLI that will print out your options and commands. We're going to use Halo 2 today. So we'll do VampIR Halo 2. Our first step is going to be to compile. And what are we compiling? Our source code is blake2s.pir. And our output, let's call it blake2s.halo2. Okay. This will take our circuit that's written in VampIR and compile it into a universal format that is then put into like a binary file called blake2s.halo2. And If I haven't made any syntax errors, that should work. Okay. VampIR does have a type system. It does some type checking. We need that in order to handle certain compositions of functions and higher order functions. So this lists the definition bool as a function from integers to integers. Okay. Yes?
Under the hood, is that transpiling to Rust and then compiling a Rust binary?
No. We use Rust. The compiler is written in Rust, but under the hood, it's compiling to basically a tree.
Okay. But it's using the Rust Halo 2 library, but at the Rust syntax tree level?
Well, for compilation, it doesn't use Halo 2 at all.
Gotcha.
Halo 2 hasn't come into the picture yet. But we're using Rust libraries and Rust data structures to represent VampIR because the compiler is written in Rust.
Yep. Cool. Thanks.
Just here is the option, and the two records. This is the format of the circuit, meaning that it is intended for the LLVM proving system.
Yes.
And another question: when we define variables, what is the set we are working on? Is it a machine word here? When we
is it a what?
Is it the 32 bits? Because the constraint x to the power 2 equal x, it's true on any field of characteristic 2. So, okay, I don't know if maybe I'm clumsy in my questions. What is where are defined the values when there is nothing else specified?
Where are we defining values?
What is x? Is it defined over n, over 2 to the power 32? What is
yeah, okay. I think I can answer that. At this stage, it is just a variable. It's just an empty hole that will get filled with some value later. Mm-hmm. When that is filled in, we already know what proof system backend we're going to use. This is later in the proving process. And basically, it'll be filled in with element of a finite field that proof system needs. But right now, it's just an empty slot.
Okay.
You can use constants. Constants are just big integers, and those will be mapped into a finite field as well eventually. But right now, you have variables and constants, which are big integers. Yeah? Okay. Yeah?
And at this point, the how-to is actually binary file, right?
At this point,
The how-to, the results of compilation, is presented as the binary file.
yeah, the result of compilation is in a binary file. It's called .halo2 because we anticipate that we may need to have some metadata there that's specific to Halo 2. But actually, I think that the representations of these binaries at this point don't actually reference the proof system at all. Okay, so let's go on to prove. So when we do prove, we are now calling the Halo 2 library to do the proving for us. What VampIR is doing is computing the witness values. Now, if you remember in this, we only have one variable, right? And that is y. But in the constraint system, things get expanded out so that this constraint x squared equals x, it's going to have multiple, well, it's going to have a value for x, and it's going to have a value for x squared, right? So VampIR is taking the inputs that the prover gives and evaluating these constraints to get the other like intermediate variables. If this were a little bit longer constraint, that would maybe make more sense. But each arithmetic operation that we do, like squaring here, is actually a new variable, and the value for that variable needs to be computed. All right, so VampIR is handling that. And then with all of those inputs computed, we send that to Halo 2, and it produces a proof. Okay, so we're going to prove we need a circuit, so -C. Our circuit is Blake2s.halo2. And we're going to put the output into Blake2s.proof. Okay. I didn't send VampIR any inputs, so it doesn't know what the prover is trying to prove with. So it's asking the prover for values. It's asking for y. That's our only variable. You can also put your inputs in like a JSON format and use VampIR that way as well. This is like the interactive version, which is, I don't know, maybe nice for a demonstration. So let's put 1 in for y. That should satisfy the circuit. Okay, it's generating proven key and proving knowledge of witnesses, etc. It says proof generation success. Proof generation success does not mean that the circuit is satisfied, because you can generate false proofs. All right, so Halo 2 took the values that we gave it, and it generated a proof using the proving algorithm, and now we have that proof. If we gave a value there that did not satisfy the circuit, we would still have a proof. It would still say proof generation success. So this proof has not been verified. Okay, so now we have a proof. Let's verify it. So VampIR Halo to verify. We need the circuit again. And we need a proof. -P tells you the proof. And remember, we put 1 in for y, so we would expect this to pass verification. Okay, yeah. So you can see here, last line, 0 knowledge proof is valid. Let's go and redo this, and we'll put something else in for y. We'll go back to the prove process and put something else in. Okay, we still got a proof out of that, but it should be a false proof. If I go back to verify, okay. VerifIR sent us an error, constraint system failure, which is what the VerifIR sends when the proof fails. Okay, so didn't work. Okay, so that's the basics of how to use VampIR and write a definition. Let's keep on going. We're going to expand our list of definitions. You can do range proofs over a certain number of bits pretty easily. If you have a smaller range proof, you can do 2 of those to get a larger range proof of double the size, right? So bool x is basically a range proof of a single bit. So if I want a range proof that is 2 bits, I can use bool twice, and then I have a range proof for 2 bits. So we're going to call this range 2. We'll have a single input x equals curly braces. And this is where we will use fresh. We've seen range 2 before. I had that as an example earlier. So what I want to do is take the first bit, or bit 0. This is actually the definition. We're going to define the first bit as bool of fresh of x mod 2. Okay? Fresh x mod 2, that will, the fresh part is just an instruction to the proving algorithm later on that B0 should be computed as the lowest bit of whatever the prover puts in for x. Okay, so it's an instruction to the prover, and then bool on the outside that actually constrains that to being 0 or 1 in the constraint system. We have these kind of like bifurcated systems. There's the constraint system part, and then there's witness generation. Fresh handles witness generation, and these expressions handle the constraints. Okay. So that should work there. Then let's get the high bit. Def B1 equals bool of fresh of x backslash 2. Backslash 2 is integer division. Okay. Something to keep in mind, because these variables are eventually elements of finite fields, there is also finite field division, which is going to work differently than integer division. Okay, so we have multiple division symbols. Okay, most programming languages have different ones, right? Backslash is integer division. Okay. So now what we have are the 2 bits. We've taken x, the input, and we've unpacked it into 2 bits. And the thing is that if x were not 2 bits, then let's see. If x were not 2 bits, we would still get values for B1 and B0, because we can still take x and mod it by 2 and divide by 2. If we want to check that B0 and B1 actually are the bits of x, not some other bits, then we need to do this constraint here. X equals 2 times B1 plus B0, and then we're going to return x. Okay. Yeah, I think I said this backwards earlier. B0 and B1 are definitely constrained to be bits, but in the proving process, technically, the prover can choose whatever values they want. We're instructing the prover to compute it in a certain way. But a proof does not have to be created by VampIR. VampIR can create proofs, but proofs can come from anybody, and they can choose whatever values they want. So you have to be careful to include all the constraints that you really mean. If we want to show that B0 and B1 are bits, we have this bool constraint. If we want to show that those are the bits of x, we have to have this kind of linear constraint down here at the bottom. Okay, yeah.
And specifically, that would be that the witness that is passed has a correct value for x, or a value for x, but the sort of virtual variables that are not represented here for fresh x mod 2 and fresh integer division 2, those values that are supplied are fake, right? Or incorrect.
Right. So all variables are, the values of all variables are computed by the prover, and they can choose whatever they want. And we're using fresh here to instruct the VampIR prover to do what we think it should do. But we always have to keep in mind that proofs can be generated elsewhere, and they still need to be correct. Yeah, like in an actual proof system, you would be deciding on the values for B0, B1, and X. You'd have to list those out explicitly. You could choose whatever. The prover can choose whatever. So we have to make sure they're constrained. Okay. Oh, I need a semicolon at the end. Okay. That looks right to me. Let's just go ahead and do the next one, range for X. Okay, we're going to do this in a similar way. We're going to have the high part and the low part. Okay, we want the high bits. These would be the low bits if we're doing mod. Let's start with low. If we want the low bits, we're taking something that is supposed to be 4 bits. We want the lower 2 bits. 2 bits is 2 to the 2 is 4, right? Okay. So we'll do this, and just copy and paste and do the high. And this is all good, except we're going to change that to integer division. And then we have x equals 4 times the high bits plus the low bits, and we'll return x. Okay? Essentially the same as the earlier one. We'll just copy and paste this whole thing and do it again to get 8 bits. And okay, so now this is going to be 2 to the 4th, which is 16, right? Okay. Now for range 16, we want, oh, wait. Guys, almost let me make this mistake. Okay. Range 8 is use 2 range 4s. In range 8, you would use 2 range 8s to do a range 16. And now we're up to 2 to the 8th, so 256. Okay. 2 range 16s give you range 32, which is what we need to do modular arithmetic. So we're getting somewhere here. Range 32 would have 2 range 16s. And now we're at 2 to the 16, so okay, 6, 5, 5, 3, 6. Yeah. Oh yeah, we have exponents in VampIR. We can just do 2 to the 16. That should work. Okay, and let's see if that compiles. Hopefully we did it all right. Ah, good. Okay, so it compiles. You can see the type checker checked these definitions. They're all functions from integers to integers. So that makes sense. Let's test this out a little bit. We'll do range 32y. I need to recompile that. I've added that. Okay. So let's do prove. Okay, we have one variable here, and it's applying range 32. So let's do. We can do hex here. So 32 bits is 8 hex characters. Yeah. So that should be the highest value that is accepted, right? Yeah? Okay, proof is generated successfully. Now let's verify it. Okay, it's valid. Let's do the proof again. This time, what just happened? Oh, I hit some key. Okay. So this time we want, let's just do one more than that. So that would be 1 followed by 8 zeros. Is that 8? Okay, proof generation success. Verify, okay. Now, obviously, if you were trying to write one of these circuits, you'd want to do a lot more testing than that. All we've tested is that there's some kind of boundary at the point where we think it is, but it does not prevent other like higher numbers from satisfying the circuit if there was some bug in there that we missed. Okay, but it seems right. Okay, cool. So now we can do modular arithmetic. So this would be mod 2 to the 32. Just one input. Okay. So if you think about what happens when you do modular arithmetic, it's actually very similar to our earlier range stuff. We're going to take x, we're going to use integer division, and then we're going to do a range proof on those results, right? Okay. So we'll do def, let's call it r for remainder. Def r is equal to x. Do fresh, x mod 2 to the 32. Okay. This doesn't constrain anything, so we need to do range 32 on top of that. Okay. All right. Then the actual constraint that we need that shows that x and r have the relationship that we expect them to is going to be that x equals 2 to the 32 plus r. No, wait, that's not quite right. We need a variable here, the quotient. So let's get our quotient. So use backslash to get the quotient. Then here's what we really need. Okay. Actually, very similar to what we saw earlier. The main difference is, almost messed that up. The main difference is we're returning r, the remainder, rather than x, right? Okay. so I guess let's do this. Z equals mod 2 to 32 y, semicolon. And let's check this out. Okay, compiled. Now when we run the prover, I've written this last line a little differently than I have before. Now we have two variables that the proof generation system is going to request from us, both z and y. And to test this out, we want to choose something for y that's, let's say, bigger than 2 to the 32 by some amount, and then check that z is the overflow. Okay. So let's do 1 followed by 8 zeros again for y. Okay, that looks right. And then z should be, what should z be? Wait a second, z should be 0, right? Because that actually is 2 to the 32. Yeah? Okay, so z should be 0. Let's see if that verifies. Okay. Pretty sure that works. Okay, so we are, we're approaching the end of our time, I believe. So let's stop there, and if anybody has any questions, let's go through it. Yeah.
So if you were to write this in Halo 2 raw, you'd probably want to do lookups for all the range checks.
Yes, absolutely.
Is there a way to expose that from VampIR?
There's yes. The answer is yes, but it wouldn't be in the VampIR language itself, because we want to keep the VampIR language as agnostic about proof systems as possible. But then the answer is you write a compiler that does it, starting from the VampIR universal representation and finding the right gadgets in the Halo 2 library that you need to use. Currently, the way that VampIR is being used here, the universal representation is like it's completely flattened out, and because of that, you lose a lot of structural information that makes it convenient to do the kind of thing that you're asking for. But there, we can also compile in a way that just doesn't flatten everything out immediately, and then you can have like lookups or other built-in gadgets. If there's one that exists for these like range proofs in the backend library, you can preserve those instead of flattening them all out, and then map them straight into the gadget that you want to use.
Cool. One other quick question. Maybe the 3 or 5 year vision for the project, is it that you have sort of transpilers or compilers from all front ends, so take Circom, Socrates, et cetera, and then you have transpilers or compilers to all back ends, and that's sort of community maintained,
Yeah.
And it becomes standard that people cross-compile these things all the time and hopefully optimize them and put in special lookup things and stuff like that.
Yeah. The vision would be that there's a spec for VampIR, and at Heliax we will write the compilers that we need, and hopefully other people will write compilers if they need something to go to a certain backend. I was just talking to a couple of projects in the other building today that, and everyone has their own custom like backend like proof systems now. Like RISC-0 has one, and the NIL Foundation has one. And what they would need to do is write the compiler for their backend. And if someone has a front-end language that they think makes things really nice, they can write a compiler from that language into VampIR and then get all the benefits of that ecosystem.
Cool, thanks.
Mm-hmm.
Just in the intro, you displayed a link to the AR to address Winterfell. Is it a possibility or is it working right now? Yeah, this pass from VampIR R script to Winterfell.
No.
Is it already implemented? No, it's a future.
Yeah.
It's a further work. Okay.
Speculative.
So right now we can compile for Plonkup, Halo 2, and Bellman. That's it.
You can compile with Plonkup and Halo 2 right now.
Plonk and Halo 2.
Yeah.
Already impressive.
Yeah, we're working on a nice back-end trait that will make it easier for people to add backends on the road.
Thanks a lot.
Okay. Is that all? All right. Thank you.